So what I want to talk about in this lesson is the idea of what are known as ionization energies. And I just want to introduce this. So ionization energies. So ionization energies. So what we can do is we can look at a particular element. So if we have a look here at sodium. So sodium is the 11th element on the periodic table. It's in group 1 and it has 11 protons. So let's just look at sodium. So if we take sodium, so Na, it has 11. And what we can do is we can look at its electronic structure. So if we take sodium, so those 11 electrons, so 2 of them are going to be in this 1s suborbital, 2 more are going to be here within this 2s suborbital. So that gives us 4, so that's 4 of the 11. So then you're going to get another 6 here, which leaves 10, and then you're going to have this 3s suborbital that will have an electron. So this is the electronic configuration for sodium, for our element sodium. Now what we know is that and we can think about this energy. So we have this energy here, and we can think about energy in terms of kilojoules. So really what we're talking about here is that each of these electrons, and we can draw it like this as well. So you can have, for example, 11 plus, and then you can have 2 electrons here, and then you're going to have the 8 electrons here. So, and then you're going to have the 1 electron out here. Let's make that one a bit better. You can have something like this. And this is just very roughly drawn. And we know that each of these are energy levels. So N is equal to 1, N is equal to, sorry, the other way around. So this would be N is equal to 3, N is equal to 2, and then N is equal to 1. Now, the way that we can look at this is we can say that, for example, these electrons here will have a particular energy value. So they'll have an energy value associated with them. If we increase the energy, what will happen is the electron, if we add energy into this, what will happen is the electron will move up into a higher energy level. It'll stay up there for a period of time. It'll come back down, and it'll give back that exact energy that we put into the system. So there's energy values associated with it. Now, when we're talking about ionization energy, like what we want to do is, if we want to turn, so sodium, for example, can turn into Na+. Now, in order for it to turn into Na+, when it's like this, it has 11, let's just change that. So it has 11 positive charges and it has 11 negative charges. In order for it to turn into Na+, it has to lose one of these. So it has to end up with something like this. So 11 positive charges and 10 negative charges. So really what you have to do is, in order to turn this into an ion, you have to get rid of this electron here. So you want to get rid of it. So what we can say here is if we want to remove this electron. Now what we can say is there's going to be a specific value associated with it's going to take energy. You're going to need energy in order to pull off this electron. And the energy that you need in order to pull off this electron is what's called the ionization energy. So that's what we mean by the ionization energy. It's the energy that it'll take to pull off this electron here. Now, so basically it's like a tug of war. So what's keeping this electron in place? Well, what you have is you have the 11, I'll keep doing that. So you have the 11 protons here within the nucleus. So these 11 protons, they're exerting an energy on the they are exerting a force on this electron here. So what they're doing is it's pulling the electrons and keeping the electron in place. So in order to pull this electron away, you're going to have to exert a certain amount of energy. And this is what's known as the ionization energy. Now, what I want to talk about, there's different types of ionization, and I just want to look at one particular definition here. So if we take, bear with me 1 second. So what we have is, and we'll just look at this first definition, and then we'll start to look at some examples of that in the next couple of lessons. So what we have is, so we have what's known as the first ionization energy of an element. So imagine we have carbon here, or sorry, we have sodium, should I say here. So the first ionization energy of an element. So what we have here is we have elemental sodium is the minimum energy in kilojoules required to remove the most loosely bound electron from each isolated atom in a mole of an element in its ground state. So imagine we have an atom of, so imagine we have a mole of sodium. So a mole, if we were to take a sample, for example, so we were to take a sample, and this is our sample of sodium, and inside that we have 1 mole. And a mole is it's just like saying a dozen eggs, for example, except the mole represents a much bigger number. So basically if we had a sample, and in that sample we had a mole of sodium, we're basically going to have a hell of a lot of atoms of sodium. So it's going to be, just to give you an idea, so it'll be 6 multiplied by 10 to the power of 23 sodium atoms. So that's 6 with 23 zeros after it. So it's a huge number. So what we're saying is that like the ionization energy, or the first ionization energy, is the energy of an element is the minimum energy in kilojoules required to remove the most loosely bound electron from each isolated atom in a mole of the element in its ground state. And when we talk about an atom, for example, being in its ground state, like if we were to take, for example, sodium, and it's just like this, the electrons are, so these 2 are here, these 2 are here, these 6 are here, and these 3 are here. It's in its ground state. Now, if I was to put some energy, give this atom some energy, what's going to happen is these electrons will become excited, and they'll move up into higher energy levels, and they'll stay there for a while, and they'll come back down and give off light. That means it will be its excited state as well. So basically what we're saying is that it's the amount of energy that we need in order to be able to pluck off the most loosely bound electron within an element, within the atoms of an element. So in the case of sodium, we'd be talking about this electron here. this electron up here. This will be the most loosely bound. So what we can do then is we can start to kind of look at some of these ionization energies. And we'll just look, just in this lesson, we'll just look at sodium. So how much energy does it take to take off that first electron? So remember, this is, we're talking about in kilojoules. So the amount of energy, as we can see here, and maybe if I make this a bit bigger, it might be more visible. So we can see here, so this is the first ionization energy for a number of different elements that are on the periodic table. So this here is the ionization energy for the first ionization energy for sodium, and we can see here that it's 400, so it's 494 kilojoules. So that's how much energy it takes in order to be able to strip off this very first electron here and turn sodium into an ion. Now again, if we think about it, there's going to be a number of factors that's going to influence this. Now if we have a look here, what we can see is as we move down a group, we can see that the ionization energy reduces. So if we look at potassium, for example, its first ionization energy is 418 kilojoules. Now that makes sense because within potassium, there's a lot more screening effect happening. In other words, like the electron is much further, the outer electron is going to be much further away from the nucleus. There's going to be more layers of electrons between the nucleus and the outer electrons. Therefore, the pulling power, or the nucleus, isn't going to have as strong as an effect on the outer electron. So as a result of that, it's going to be easier to take that, to whip that electron off. Now, if we have a look up here at hydrogen, for example, its first ionization energy is 1,310 kilojoules. So it is 1,310 kilojoules. So that's it's significantly bigger than, for example, the example that we're looking at, sodium. And that makes sense. If you think about it, you have a +1, so you have one nucleus, and then you have this one energy level, and then within that you have this one electron. So you can see here that this electron, which is negatively charged in hydrogen, is much closer to the nucleus, so therefore the nucleus has a much stronger grip on it. So in order to be able to pull this electron off, in order to be able to induce the first ionization energy, you're going to need a lot more force than if you're trying to pull this off, because this is much further away from the nucleus, and there's also a screening effect happening from all of these electrons that are in between the nucleus and it. So you can see that as you move down the group, the ionization energy reduces. Now also as well, you can see that as you move across, there's a particular pattern with it as well. The ionization energy in some cases increases. And again, that makes sense as well, because as you move across, the screening effect is going to be the same. For example, for like if we look at magnesium, for example, the ionization energy jumps up to 736. Now that makes sense because magnesium has more protons, so it's going to have more of a positive pulling charge on its outer electrons, but also as well the screening effect is going to be the same for sodium and for magnesium. And as you move across, we can see that as we start to gain some electrons, that starts to kind of reduce then as well. But we'll look at that in a little bit more detail as well. So again, this is just a quick introduction to this idea of what's known as ionization energies and what we mean by an ionization energy. So basically, it's the energy that it takes in order to be able to turn a neutral element or atom of a particular element to turn it into an ion. Okay, so hopefully that makes sense, and thank you for listening.